very happy to have today. We are very happy to have two talks by two leading mathematicians, and the first one will be Christopher Hacon, and the second one will be Ngo Cho. And so it's my great pleasure to introduce Professor Christopher Hacon as our first speaker. I guess most people in algebraic geometry know the work of Hacon, especially on model program, biological geometry, the work of BCHM. Yeah, lots of work that you should have read of his work. And we are very happy today that he's going to talk about his work in progress. And the title today is the boundedness of polarized Calabi-Yau fibrations and generalized pairs. So please, Christopher, thank you.
Oh, thank you very much for the introduction, and thank you very much, everybody who's attending. I guess let's get started. So sort of start from introduction. According to the minimum model program, algebraic varieties, and for the experts, more generally, log canonical pairs, can be classified in terms of three main building blocks. And these building blocks are higher dimensional generalizations of Riemann surfaces of genus 0, 1, and genus greater or equal to 2. So let me give some definitions. With XB, I will denote typically I'll denote a log canonical pair. So if you don't know what a log canonical pair is, you should think that X is a smooth compact manifold, and that B is a divisor with simple normal crossing. So a bunch of codimension 1 subvarieties meeting transversely. And if you're an expert, of course, you know what a log canonical pair is. Then we say that this pair XB is a log canonical model if the log canonical class, if the class of KX plus B corresponds to an ample divisor. It's log Calabi-Yau if the class of KX plus B is numerically trivial or equivalently Q-line equivalent to 0. And we'll say that XB is a log Farnell pair if minus KX plus B is ample. So these are sort of the three important classes, the three building blocks of higher dimensional varieties. One of the most important objects to consider is the log canonical ring. So the log canonical ring, denoted by R of KX plus B, is the graded ring, which in each graded piece keeps track of the global sections of the corresponding tensor power of the log canonical line bundle. So M is a positive integer, non-negative integer, and we consider the divisor M KX plus B, and we consider the space of global sections. And this way we obtain a graded ring. Now, it's an important conjecture that this graded ring is finally generated. It's known, that's known to be the case. It's known that it's finally generated in many cases. For example, it's known to be finally generated if the pair XB is KLT. Again, for the non-experts, just pretend that X is a smooth variety. That's a smooth manifold. That's already a very interesting case. And also, it's very easy to show that this ring is finally generated if, for example, KX plus B is semi-ample. Semi-ample here means that a multiple becomes base point free. Looking at this log canonical ring, one can extract from this several important invariants. So, for example, we can consider the dimension of each graded piece, and the dimension of these pieces behaves like a polynomial. So let me denote it by PM, roughly behaves like a polynomial. So the Kodaira dimension is the degree of this polynomial. Now, if each one of these vector spaces is empty, so for example, for P1, then by convention, we set the degree of this polynomial to be minus infinity. And otherwise, the degree will be an integer between 0 and D, where D is the dimension. So the degree of this polynomial can at most be equal to the dimension of the variety. So in the case of Riemann surfaces, in the case of curves, the Kodaira dimension can be minus infinity, 0, or 1. It's 1 precisely when the genus is greater or equal to 2. And the other interesting number that one can extract is the leading coefficient of this polynomial. So the log canonical volume is the coefficient of m to the d, the coefficient of the highest order term. Remember, this is a polynomial of degree at most d, so we're looking to the coefficient of the leading term. Of course, sometimes the volume could be 0, the coefficient of the leading term could be 0, in which case we look for the coefficient for the first non-zero coefficient, and we declare that to be the Ithaca volume. Okay, so once again, just to emphasize, the volume will be positive. That's if and only if this polynomial has maximal degree. So if and only if the Kodaira dimension is equal to the dimension of the variety, is maximal. And in this case, this is an important case, we say that the pair is of log general type. Okay, so in the case of log general type, the one of the important results is that again, so the statement that I'm giving here is a bit a statement for experts. So if you're not an expert, you can completely ignore this DCC set. If you're an expert, then we will be considering pairs XB, where B is a divisor whose coefficient belong to this DCC set. So we fix a DCC set for the coefficients, we fix an integer d for the dimension, and we fix a positive constant v for the volume. Then the set of all log canonical models of that given dimension, whose coefficients are in the given DCC set and whose volume is this fixed positive constant v, then this set is bounded. So what does it mean that the set of these log canonical models is bounded? Well, that would be the last line here. Boundedness just means that all of these log canonical models can be parametrized by a projective family. So we'll have a projective morphism from x to a base t, which may have many, many components. And we'll have a divisor b on x. And every one of these pairs xb appears as one of the fibers of this projective morphism. So that's the meaning that these pairs are bounded. DCC set I didn't really explain. It's a set satisfying the descending chain condition. So that means that any non-increasing sequence is eventually constant. The typical DCC set is the set of the form 1 minus 1 over n, where n is any integer. So it has accumulation points from below, but not from above. And I think I mentioned it before, but just in case, a log canonical model is a pair with log canonical singularity such that the canonical class kx plus b is ample. So that's a log canonical model. And once again, if we fix the dimension and we fix the volume, then these belong to a bounded family. So that's sort of a very nice results for varieties of general type, but the focus of this talk is more on what happens for varieties of intermediate Kodaira dimension. Okay, but before I get to intermediate Kodaira dimension, let me recall what happens in the phenotype case. So that's Kodaira dimension minus infinity. There's a famous result of Birkar, also known as previously known as the Borisov-Alexev-Borisov conjecture, which says the following. Suppose that we fix, once again, the dimension, and now we're also going to fix a positive constant epsilon, whose purpose is to somehow bound the singularities. Then the set of all projective varieties such that the dimension is this fixed integer d, and xb is an epsilon log canonical pair. I'll explain that in a second. And minus kx plus b is ample, so it's of phenotype. Then the set of these varieties is bounded. So what does epsilon log canonical pair mean? Well, for example, any smooth variety will be epsilon log canonical, but in general, it means that all of the discrepancies, at least of the log discrepancies, are bounded below by this positive constant epsilon. So if you're not familiar with that, maybe think about smooth varieties or think about varieties with terminal singularities. So varieties with terminal singularities will be one canonical, in fact, not just epsilon log canonical. So we have two very satisfactory answers in these extreme cases, in the case of log canonical models of general type, and in the case of Fano varieties. And the question is, well, does that mean that we understand everything in between? And actually, I'm going to make the argument that we don't understand much for the case in between. The Calabi-Yau case, for example, is still wildly open. How widely open is it? Well, here's a conjecture which is about 50 years old due to Yau. Consider the set of Calabi-Yau freefolds. So in this case, you can even assume that the canonical line bundle is actually linear equivalent to the trivial line bundle. Then the question is, does this set have finitely many topological types or not? There will definitely be infinitely many families. The easy examples show that there are infinitely many families. Even already in dimension 2, you have infinitely many families of K-free surfaces. But these K-free surfaces will belong to one analytic family, so they have the same topology. Is something similar true in dimension 3? And as you can see, this is a really old conjecture, almost as old as I am, and we still don't know the answer. So a lot is not known for Calabi-Yau varieties, even in dimension 3. So I'm going to now sort of somewhat discuss the intermediate Kodari dimension case. So let's suppose that we now consider log canonical pair with Kodari dimension not maximal, but also strictly greater than 0. So somewhere in between. Conjecturally, it's expected that this pair will have a good minimal model. So there will be, up to birational isomorphism, there will be a modulo of xb such that kx plus b becomes semi-ample. And in particular, the corresponding ring is finitely generated. And this is what the next line says. After performing finitely many flips and divisorial contractions, if the conjecture is true, then we can assume that kx plus b is semi-ample and defines a morphism. And this morphism is known as the Ithaka fibration. So that will be a morphism from x to z, and it has certain important properties. So the first property is that the dimension of the target, z is just given by proj of the pluricanonical ring. So the dimension of the target is the Kodari dimension of the pair xb. And if we consider a general fiber of this morphism, then a general fiber is a log Calabi-Yau. So if I take the canonical class kx plus b and restrict it to the general fiber, then I will actually get the canonical class of the fiber plus bf, and that will be linear equivalent to 0. So it will be a log Calabi-Yau. And so we'll call these log Calabi-Yau fibrations. And one of the open questions is to understand these log Calabi-Yau fibration in as much detail as possible. Of course, if we don't fully understand log Calabi-Yaus, then sort of we have to, the best that you can hope to say is that, maybe if you understand the general fiber of the Ithaka fibration, then you also understand the Ithaka fibration. So I'll try to explain some of the difficulties and some of the positive results that we have so far in this area. Okay, so the first thing that we typically use to study these log Calabi-Yau fibration is the famous Kawamata canonical bundle formula, which says that in the above situation, so if you have a log Calabi-Yau fibration, then you can write the class of kx plus b as the pullback of something similar. Well, so here you see that I have another pair, another log canonical pair, in fact, kz plus bz, but there's also a moduli part, mz. So let me explain these terms a little bit. So what you should take from this Kawamata's canonical bundle formula is that somehow the geometry of the pair xb can be understood in terms of geometry of a triple on z on the base. The triple has, well, the canonical class of z, a boundary part bz, and a modular part mz. So the boundary part, bz, measures the singularities over codimension 1 of this fibration. So the formula, it's not too complicated, but it's defined in terms of certain invariants known as log canonical threshold. But it's very easy to sort of understand what the rough philosophy of the definition of bz is. It keeps track of the multiplicities of the fibers, roughly speaking. So if you have a fiber, let's say you have a smooth fiber, which appears with multiplicity m, then the corresponding coefficient of bz will be something of the form 1 minus 1 over m. So again, you see that even if you even if B was 0, so this would be in the case where B is 0, even when B is 0, you see that all of a sudden these coefficients in a DCC set, in the set 1 minus 1 over M, naturally appear. So, even if you're after a nice statement about smooth varieties, you're very quickly led to consider log canonical pairs, or at least KLT pairs. The component MZ instead is known as the moduli part, and it's supposed to measure the variation of the fibers of these pairs FBF in the corresponding moduli spaces. So remember, I'm assuming that we have a log Calabi-Yau fibration. So these fibers are log Calabi-Yau, and their moduli spaces are expected to be well behaved. If the boundary part is 0, if this BF is 0 and the fiber is an elliptic curve, then the moduli part will just be the pullback of an ample Q divisor via the J function. So it's what you expect it to be. And the nice thing about this moduli part is that in general, it's a Neff divisor, roughly speaking. So if you compute this moduli part on a sufficiently high module of Z, if you sort of prepare the morphism, then you can assume that this moduli part is actually a Neff divisor. And then you can make sense of the singularities of the pair Z, BZ plus MZ. It will have what are known as generalized log canonical singularities. I'll say a few words about that in a second. But roughly speaking, you should imagine that on a high enough model, MZ becomes semi-ample, has no base locus. So really, we're talking about the singularities of Z and BZ, and MZ is just sort of a positive divisor that works in your favor, so to speak. So let me say a few more precise words about generalized log canonical pairs. So first of all, sort of just general background information is that generalized log canonical pairs are indeed playing an increasingly important role in birational geometry. Many important, interesting results are proven using generalized pairs. For example, Birkar's work on the BAB conjecture makes extensive use of generalized pairs. By definition, a generalized pair, so they arise typically in the Kawamata's log canonical bundle formula, but they arise in many other contexts. And so formally, a generalized pair, which I'll just denote by G pair, consists of a normal variety X, a boundary divisor B, and a BNF B divisor M, such that KX plus B plus MX is R Cartier. So that's a technical condition, again, completely expected to experts. If you're not an expert, I just suggest that you think of X as being a smooth variety, in which case this R Cartier condition is automatically satisfied. And I just suggest that you think of M as being a Neff divisor itself, and B as being a simple normal crossing divisor. So how do I check? So first of all, the name is slightly confusing because it's a generalized pair, but actually there are sort of three objects to consider, right? There's X, B, and M. But the name is what it is. So how do I make sure that a generalized pair has generalized log canonical singularities? What I need to do is I need to go to a sufficiently high log resolution. So I need to perform enough blowups to ensure that the strict transform of B will have simple normal crossings, but also that the moduli part becomes an honest Neff divisor, which descends to that model X prime. So once I have a sufficiently high log resolution, I can compare the pullback of this R divisor of KX plus B plus MX with KX prime plus BX prime plus MX prime. So MX prime is given. This formula actually defines BX prime, right? BX prime is obtained by taking the difference between KX prime, MX prime, and this pullback. And we say that this pair is generalized log canonical if the coefficients of this boundary part that's been defined by this formula are less or equal to 1. So we have at most logarithmic poles for this log canonical class. So it's just the analog of the definition of log canonical pairs in the usual setting. As I was saying, these generalized log canonical pairs arise in many contexts, especially using Kawamata's canonical bundle formula, but also they arise in the case of final varieties. So for example, if you have a final variety, say a log canonical pair such as minus kx plus b is ample, or even just nef, then I don't know, you could take the modular part, for example, to be minus 2kx plus b. So this will be an F divisor. And then x, b plus m will be a generalized log canonical pair of general type, right? Because if you compute kx plus b plus m, that will be linear equivalent to minus kx plus b, which is ample. So in a natural way, whenever you have a final variety, you obtain a generalized log canonical pair of log general type. So results on varieties of on generalized pairs of log general type also give you results on final varieties. So it's an interesting way to look at the problem of final varieties. And as we've seen, if you have intermediate Kodaira dimension, you're also going to look at the Ithaka fibration, which gives you another kind of generalized log canonical pair. So pretty much the upshot is, whenever you're considering pairs which are not of log general type, then you end up considering generalized log canonical pairs of log general type. Now, on the one hand, we expect generalized log canonical pair to behave quite similarly to log canonical pairs, but there are also some key differences. So let's start with some similarities. So suppose that we have a generalized Kawamata log terminal pair, or maybe even generalized DLT pair. So this is slightly better singularities than you would have in the log canonical case. Then given any ample divisor A, you can think of, so suppose that M is a F divisor, for example, then M plus A becomes an ample divisor. So I can pick an R linear equivalent divisor such that Kx plus delta is a KLT pair in the usual sense. And so an immediate consequence of this is that for, at least for generalized DLT pairs, we can run the minimal model program with scaling. Many of the techniques from the minimal model program will apply to this context. Of course, we don't know that this minimum model program will terminate in full generality, but we have the same problem with the usual pairs. So from this point of view, generalized DLT generalized pairs behave very similarly to the usual pairs. And in fact, one can go even a little further. By a recent result of myself and Jihao Liu, we were able to prove that flips and divisorial contractions also exist in the log canonical case for generalized log canonical pairs. So you can actually run a minimal model program even for generalized log canonical pairs. So really, from that point of view, we're in a very similar situation to the case of usual pairs. But what are the differences that we expect? Well, for one thing, the ring, pluricanonical ring, will not be finitely generated, especially in the log canonical case. In the KLT case, there are many instances in which it will be finitely generated, but in the log canonical case, it's rarely finitely generated. And also abundance is not expected to hold.
Excuse me, sorry, Christopher. So can you show the final generation for the general case? I mean, I know that if kx plus b plus m is big, so we can do the perturbation, but you can do the more Fujinori technique for the generalized pairs.
No, so okay, so as written here, it's not quite correct. I think that's what you're objecting to. You. So I should have written it's okay for big divisors in the G KLT case.
Okay, sure, yeah.
Yeah. So it's not okay in full generality. So there are many instances in which it works out in the generalized KLT case, but one has to be careful. Yes.
Thank you.
And in the log canonical case, it's most often not true that this ring is finitely generated. And also abundance is sort of, at least unless you state it very carefully, it's trivially false. For example, consider an elliptic curve, trivial boundary, and pick for your F divisor let's pick a non-torsion element in pick 0 of x. And then you know, this will be the generalized log canonical class will be this mx, which is nef, but it's not semi-ample. So of course we can't expect abundance to hold in full generality. This example would lead you to think that maybe abundance holds up to numerical equivalence, but that's also not quite clear. Okay, here's another example of a positive result for generalized pairs. So this is a result about birational boundedness of generalized pairs of general type. So we're going to fix, it's a theorem of Birkard and Zhang. We're going to fix the dimension. D is a positive integer that stands for the dimension. And we're going to fix a DCC set phi for the coefficients of B. And we're going to fix the B Cartier index R for the modular part M. Okay, so we fix D, R, and phi. And then there will be an integer M, depending only on these three quantities, such that if we consider a generalized log canonical pair of the correct dimension of X is D, with coefficients in this DCC set, such that Rm is Nef and Cartier, and of course, we're going to assume that Kx plus B plus M is big, so it's a general type, then this fixed multiple of this log canonical class actually defines a birational map. And in particular, that tells you that the volume of this class is bounded from below by this universal constant, 1 over m to the d. So that is sort of a very similar result to the case where you have just usual log canonical pairs. However, even though we have such a nice result for birational boundedness, actual boundedness of generalized log canonical pairs is a much more subtle question. So I'm going to have a long worked example in a few minutes to show you why you should expect it to be a subtle question. So let me start with a computation. This example is going to take about 3 slides. I apologize for the length. The first slide is a rather classical computation on surfaces. So let's start with that. So I consider an elliptic curve, a smooth elliptic curve in P2. I pick 9 points on E. The sum of these points could be torsion or non-torsion, and we'll have different behaviors if it's torsion or non-torsion inside the group of this curve. So anyhow, elliptic curve, 9 points, and I consider the blow up of P2 along these 9 points. Now, E prime denotes the strict transform of this elliptic curve, and that's actually linear equivalent, it's easy to see, to minus kx, right? Because k of P2 is linear equivalent to this elliptic curve, and then we blow up these 9 points. And now maybe I'll focus first on the case where these points are, the sum of these points is torsion on the elliptic curve. So let's assume it's m torsion, where m is a positive integer. In this case, it's known that there exists a curve of degree 3m, which has simple singularities of order m along each one of these 9 points. So essentially, the elliptic curve E and C intersect transversely at these 9 points. And just to keep track of the fact that the sum of these 9 points is torsion, I'll denote x by xm to remind myself of the order of torsion. So given this, the existence of this curve, it's then easy to see that minus kxm is in fact semi-ample, and it induces a morphism to P1. And this morphism is just induced by the pencil given by m times this strict transform of the elliptic curve and the strict transform of this other curve C prime. This was a curve of degree 3m going through each of these points with a singularity of order m. So this gives me a base point free pencil and hence a morphism to P1. And the interesting thing about this morphism is it has one fiber of multiplicity m corresponding to this m times E prime, and then all other fibers are actually smooth. Now I'm going to write down a nice generalized pair. So just as I suggested before that we could do, I'll consider for my NEF divisor, I'll consider minus 2kxm. It's even better than being NEF. In this case, it's semi-ample, right? Okay, so when I consider kxm plus m, so this is a generalized pair, it's with mild singularities, it's KLT, and I can apply, restricted to every fiber, this is trivial divisor, so I can apply Kawamata's canonical bundle formula to this morphism Fm from xm to P1, and it's a easy computation. Actually, I think I got it wrong. Oh no, that's correct. So kxm plus m would be linear equivalent to minus kxm, right? Minus 1. And if you look at minus m kxm defines the morphism, so this will be Q-linear equivalent to the pullback of 1 over m. And if you want to write down Kawamata's canonical bundle formula, well, okay, so we had a fiber of multiplicity m, so that means that the corresponding point on P1 appears with coefficient 1 minus 1 over n, 1 minus the log canonical threshold. Then we have the part corresponding to the canonical line bundle on P1, which has degree minus 2, and hence the moduli part has to have degree 1 plus 2m, so that everything works out to have degree 1 over m. At any rate, this tells us that the Ithaca volume is 1 over m. So the Kodaira dimension is just one of this pair, right? It defines a morphism to P1, and the Ithaca volume is 1 over m, which is not bounded from below. I can pick any m I want, right? This could be torsion of any order. And so these Ithaca volumes go to 0. So Birkar and Zhang's theorem said that in the case of general type, the volumes were discrete, in fact, bounded from below, but that's not the case for the Ithaca volume. So something more interesting is going on in this intermediate Kodaira dimension case. And moving to the non-torsion case, in the non-torsion case, these curves do not exist, so we do not have a pencil, we do not have a morphism to P1, and in fact, we obtained that minus kx is NEF, but it's not semi-ample. So we have this sort of dual behavior. Whenever the sum is torsion, we have a semi-ample divisor. Whenever it's not, it will not be semi-ample divisor. And we can put all of this in a family. So think, for example, let's fix the first 8 points and let's vary the 9th point in the complement of these 8 points on the elliptic curve. Let's call that T. So we get a nice family over T, and the corresponding M will be the NEF divisor corresponding to minus 2kx. So the corresponding generalized log pair will be NEF over T, but it won't be semi-ample over T because it's not semi-ample on a dense set of fibers. And consequently, it's not a good minimal model. And in fact, the NEF reduction map is quite badly behaved, if you know what the NEF reduction map is, because there's sort of this mixed behavior. There are countably many fibers for which the NEF reduction map wants to be a map down to P1, and there are uncountably many fibers for which the NEF reduction map just wants to be the identity. So it's a bad example, sort of similar to these examples of Lesoutre and of the name of the co-author is escaping me right now. Sort of a bad NEF reduction map for these examples. And maybe notation-wise, it's useful to introduce a very ample divisor A on X. So you can pick your favorite very ample divisor, but one easy choice is to take 2 times the strict transform of the elliptic curve minus 1 times the sum of the exceptional divisors. So F denotes the sum of all the 9 exceptional curves of this blow-up map from P2 to X. And then one easily checks that A is actually a very ample divisor of self-intersection 27, if you want to know. It's not important that it's 27. So then we can consider, so now I'm going to construct a 3-dimensional example with some interesting feature. And the 3-dimensional example corresponds to the blow up of a cone over this surface X. So let's take the following P1 bundle. we're going to take the P1 bundle corresponding to O of X, direct sum O of X of this ample line bundle. And H will denote the tautological line bundle. So, of course, we have a projection down to X. And by the usual computation, if I consider, I'm going to think of X, I'm going to identify it with the negative section of this projection. So, and then I'll think of the tautological line bundle as another section which does not intersect X. And then when I write down the formula Ks plus X plus H, then that actually corresponds. So the restriction to any fiber will have degree 0. -2 plus 1 plus 1 will have degree 0. And in fact, this will correspond to the pullback of the canonical class on X. And I'll denote by X to V the map to the cone. So this divisor H, this tautological line bundle, is semi-ample, and it defines a morphism down to the cone where we contract this negative section X gets contracted to a point. Okay, so what I want to do is maybe I'll give you a heads up of what's going on. So in the case that we have that this sum of points is torsion, that we're considering one of these XM, then we can sort of construct out of this diagram, we can construct an interesting flip. But in the case when the sum of the points is not torsion, this flip doesn't exist. So this sequence of flips will turn out to be will give us an unbounded pair of log canonical, an unbounded sequence of log canonical models. So let me try and make this precise. Okay, so let's remember that V is the cone and X is the P1 bundle. This should be S. So S is the P1 bundle over the surface X, and this should be the projection from the P1 bundle to the cone, which is defined by H. So my apologies again, this X should be S. So I can consider the log canonical model of S comma X over V. And this is just a traditional log canonical pair, and it's easy to check that this ring is finally generated. So we contract certain curves, we contract, in fact, the divisor X, and we'll get a log canonical model over V. But now, if the sum of these points is M torsion, then let me consider minus Ks plus X. So this will be the pullback of this it will be the tautological class minus, of course, Kx plus X plus H, which I can rewrite as H minus the pullback of Kx. Okay, so H is semi-ample. In fact, it defines the morphism to V. And remember, minus Kx itself was semi-ample when we are in the M torsion case. So this whole divisor is semi-ample. So it must define a morphism to a variety U over V. And what does this morphism do? It contracts the negative section X precisely to this P1 curve, which I denote by Z, right? Because H is 0 precisely on X. H restricted to X is 0, and it's ample everywhere else. The pullback of Kx restricted to X, again, is Kx, and minus that defines the morphism to Z. So it's really easy to check that we have that this map from S to U contracts X down to this curve Z. And similarly, it's a trivial computation to see that Ku times Z will be minus 1 over M. So we get a flipping contraction. Now, none of this works if the sum of the point is non-torsion. This U just doesn't exist. And so for these countably many points, the U exists, but it does not belong to a bounded family. In fact, it can't belong to a bounded family, right? Because the intersection with these smooth rational curves is minus 1 over M. So the Cartier index of Ku is also not bounded. It's 1 over M. It goes to 0. So these examples, these UM, cannot belong to a bounded family. On the other hand, when I perform the flip, I get the variety U plus discussed before, which does belong to a bounded family. So we have this weird situation in which we have an unbounded sequence of varieties, which after I perform a flip becomes bounded. And now, if we consider them as generalized log pairs of log general type, then we have, in fact, these UM are in fact a sequence of generalized log canonical models, which is not bounded. So in the KLT case, we do expect some boundedness results, but the strong boundedness results cannot hold in the generalized log canonical case. On the other hand, if we blow up the flipping curve, if we go back, instead of considering U, we consider S, then we do have a bounded family. So maybe in the generalized log canonical case, instead of considering honest boundedness, maybe we want to consider boundedness up to Krepet maps in codimension 1. So maybe this phenomenon that we have to actually blow up something, extract a divisor, is what's really necessary to have some boundedness statements. So in other words, maybe we can't expect the log canonical models to be bounded, but maybe we can hope that there is some choice of minimal models that belongs to a bounded family. Okay, so let's now move to some positive results. So let's now consider return to the question of actually bounding the good minimal models of log canonical pairs of intermediate codaric dimension. So once again, I consider the Ithaca fibration. And how could I hope to bound this Ithaca fibration? Well, maybe if for some reason we can bound the fibers, so these log Calabi-Yau varieties, and also we can bound the base, then we can sort of view this variety of intermediate codaric dimension as being built out of these fibers and the base. So maybe if we know the boundedness of the fiber and the boundedness of the base, we can conclude boundedness of this variety of intermediate codaric dimension. In fact, to be a bit more precise, if we can if the fibers belong to a bounded family, then really we should be able to reconstruct XB from the moduli space of those fibers. In fact, XB should be determined by some map from the base Z into the corresponding moduli space. And this map in turn should be determined by the moduli part by MZ, right? So if I can get a hold on, for example, let's say bound the degree of MZ in some interesting way, and I can bound the fibers so I know what moduli space I'm mapping to, then in some sense I should be able to bound these varieties of intermediate codaric dimension. Okay, so as I said, though, bounding varieties of log Calabi-Yau varieties is almost an impossibly hard problem. So what we want to do is we want to actually fix a polarization. So if we fix a polarization, if we a relative polarization for XB over Z, so a divisor A on X such that its restriction to the general fiber is ample, and we assume that the volume, the corresponding volume, so KF plus BF is numerically trivial, plays no role here. The volume over AF is a fixed constant, say U, then these fibers will be bounded essentially by a Hilbert scheme argument. Now, in order to bound the base, I will similarly need to fix the volume of the base, right? Because if you don't fix the volume of this pair of log general type, it's a bit like if you consider curves of genus G, if you don't fix the genus, then there's no chance that they belong to a bounded family. So I do want to fix the volume of KZ plus BZ plus MZ, and that's the same thing as fixing the Ithaca volume of KX plus B. Okay, so essentially, I'm now going to discuss a theorem of Jiao that essentially says that once we fix those two quantities, then we do get a boundedness result up to isomorphism in codimension 1. So before I explained why it's really necessary to work up to isomorphism in codimension 1, and so in some sense this is an optimal result. So what are we going to try and bound? So remember I said that we should fix the volume of the fiber and we should fix the volume of the base. So let's fix the dimension. Let's fix the set of possible coefficients in a DCC set phi, and let's fix U and V, the volume on the fiber and the volume of the base. So now I'm going to consider G KLT D phi UV. So this will be the set of all d-dimensional projective KLT pairs XB, such that the coefficients of B are in this DCC set phi. I didn't write it. Oh yeah, the dimension of X is D. The Ithaca volume is V. Kx plus B is semi-ample, inducing this fibration. So this is the Ithaca fibration. And there's an integral divisor on X such that its restriction to the general fiber is ample with fixed volume. The volume is U. Okay, so I'm bounding the fibers and I'm bounding the volume of the base. Then Joule's theorem says that the set of all of these KLT pairs, notice he's restricting to KLT pairs, not log canonical as we were hoping, this is bounded up to Crapamp birational isomorphism. So we allow the possibility not only for two things to be sort of birational codimension 1, but we may need to actually blow up a divisor, just like in the example that I discussed previously. So when you first see this, you say, oh, maybe this is almost obvious because after all, I have this relatively ample divisor with bounded volume. But the volume is only bounded on the fibers. In order to conclude, you really need to produce an actual ample divisor whose volume is bounded on the whole of X, not just on the fibers. Therefore, what we really need to do is we need to replace this relatively ample line bundle by some globally ample line bundle of bounded volume. And this is a non-trivial problem. So the main intuition behind the proof is as follows. Well, first of all, we have assumed that A, at least on the general fiber, the restriction of A is a relatively ample divisor of bounded volume. So by a Hilbert scheme argument, we expect that there is a parametrizing family for all of these fibers. So then if I denote the parametrizing family by XB over H, then at least over the generic point, XB to Z should be obtained by base change from a map to H. Now, notice that the way I've written it, I've now forgotten about this polarization A. So if I just consider this as a map from XB to H, then this may not have maximal variation. So I do this, the usual trick that you do to reduce a question to a question of maximal variation. So after some generically finite base change, there will be a morphism down to a variety, let's say H sharp. The dimension of this variety is the same as the variation of this fiber space, and this fiber space will be induced by base change from this fiber space. So if I pull back this family to H prime, and if I pull back this family to H prime, they will be birationally isomorphic. They will be birationally equivalent. Okay, so this is exactly what Ambro does when he discusses the moduli part of a given log canonical fibration. Okay, so, well, maybe I need to go back to the picture so it's easier to follow. So the moduli part of this fibration will just correspond to is determined by this map over an open subset. So in fact, it would just be the pullback of the moduli part of this fibration, and the moduli part of this fibration is sort of once we pull it back to H prime, corresponds to the moduli part of this fibration of maximal variation. So now, from the bound on the Ithaca volume of Kx plus B, we're able to bound the degree of the map. Well, Giao is able to bound the degree of the map, roughly speaking, from Z to this moduli space. Let's think of it as a moduli space, H upper shriek. So that allows us to reconstruct in finally possible ways this this fiber space from this fixed fiber space and the space of all possible morphisms from Z to H shriek. So that's a sort of a very intuitive and basic idea. The proof is actually very technical, very technically involved. So I apologize for not being able to give more details of the proof. But anyhow, maybe roughly speaking, maybe more intuitively, we construct this diagram, and the new ample divisor is obtained by, what do? We take the ample divisor on this fibration, and we essentially pull it back to the map from XB to Z. At least in the case that this map has maximal variation, that is essentially what's happening. Unluckily, Giao theorem does not work for log canonical pairs, but at least from preliminary investigations, it seems that we should be able to prove similar results in the log canonical case. But at least in the meantime, we can show that jointly with Cochet-Birkard, we can show that if we consider the log canonical case, when we look at these generalized pairs that we get via Kawamata's formula, ZBZ plus MZ, then these actually belong to a bounded family. And in particular, we can control the volumes of the moduli part, and we can hope to control, to use that to control the whole geometry of XB. So we're expecting to generalize Giao's result to the log canonical case. And I think I'm out of time, so thank you very much for listening. And if you have any questions, I'll be happy to try and answer them.
Okay, yeah, thank you very much for the talk. Thank you. So are there any questions?
Can I ask some question?
Of course.
So you said unboundedness for the generalized. We cannot expect the generalized version of this theorem, right? By the giving example.
Yes. So
yeah.
Strong versions of boundedness for generalized pairs are likely to fail.
Yeah. I mean that I think that. So when we consider the generalized pairs as such kind of things, you didn't bound the dimension of X because so base of the canonical bounded formula is a generalized pair basically. So
right.
So the unboundedness result is very natural. So my question is that so you are generalized pair is so consider the full generalized pair. I mean all negative polarizations, but coming from the polarization coming from the canonical boundary formula is more special, like the Kaji-log pairs, normal Kaji-log pairs. I mean, my question is so you are bounded on this condition really needs the fixed dimension of X. I think we need the dimension of Z, but still we need to consider the fixed dimension of X.
Okay, so if I understand correctly, your statement is maybe in this theorem, that the last theorem I stated, not Giao theorem, but this theorem here, maybe we do not need to fix D, the dimension of X, but maybe it's enough to fix D, the dimension of Z.
Yeah.
And yes, you may be right about that. However, there is one little kink, because now the kind of arguments we use, we really need boundedness of the fibers to make our conclusion. And so fixing the dimension of D allows us to ensure that the dimension of the fibers are also fixed, right? Mm-hmm. So if we don't fix the dimension of the fibers, then there will be infinitely, the fibers won't be bounded. So we could run into trouble a priori. So
yes.
It's a good question. Can we actually just fix the dimension of z, or do we really need to fix the dimension of x? And I don't know the answer, but I will be a bit scared of claiming that I can just fix the dimension of z.
So I'm feeling this. So full generalized pair is a very subtle object, but restricting on the normal Kaji-log pair, which should be the generalized pair, but modular part is very good for the such thing. So some good result in the minimum mobile problem can be expected for the normal Kaji-log pairs. I think that, yeah. Just I ask you. Yeah.
Well, I agree. So for example, we expect this moduli part to be semi-ample, right? In this case.
Yeah.
So it should definitely be much better behaved.
Thank you.
Excuse me. So, hi. So, my question is, I could not follow the technical details, but my question is that can it recover the result of all the result of gross?
So I think if I remember correctly, Gross's result is so which result? This is the result.
Vibration.
Yes. So I want to say yes. So but I don't remember the exact statement of Gross's result. So in a lot of these statements, we need to fix some multi-section or something like that. And fixing a multi-section is analogous in this case to fixing this relatively ample divisor of fixed volume. So the volume of the ample divisor sort of corresponds to the degree of the multi-section. So I suspect that this does recover, at least in part, Gross's old result, yes.
Yeah, so yeah. So if you can state also to the classical non-log, so application to non-log, how much you can apply to non-log classical case, then it will be more accessible to non-expert like me. So.
Yes, maybe I should have emphasized more the classical.
How much can you? Yeah. So then, how much can you generalize Gross's result for non-log situation?
Well, so in some sense, we're saying, okay, so this condition about multi-section of bounded degree is being replaced by having a relatively ample line bundle of bounded degree on the general fiber. And once we have fixed that, and once we fix the Itaka volume of Kx, which is the natural thing to fix when you're considering an Itaka vibration, right?
So if you assume that the total space is just Calabiao at the beginning.
Oh, well, okay. So if you assume that the total space is Calabiao, then what these kind of results are saying, the Itaka vibration will just be a map to a point. So you're just considering the geometry of the Calabiao pair. And what you need to do is you need to fix it. So you're saying something about polarized Calabiaos. So if you fix a polarization of bounded degree on a Calabiao, then it will belong to a bounded family.
Okay, thank you very much.
Thank you very much. So are there some more questions? Okay, so if not the case, let's thank the speaker again. Yeah, thank you very much, Crystal.
Thank you very much, and hope to meet all of you in person one of these days.
Yes, yeah. Hope to see you soon in person soon.
Yes, definitely. Bye-bye.
Bye. So our next talk will start in 15 minutes. Okay, thank you.